Firstly, thank you all so much for coming today. The weather is not the best, but I guess representative of the British weather that we like to enjoy. But I'm going to get the sort of boring bits out of the way first. So in terms of housekeeping, so hopefully if you haven't been already, you may have seen some of the toilets. So if you go straight out the doors, there's bathrooms on the left and right. But there's also more bathrooms by the reception where you came in. We are not expecting a fire. There is no chemistry currently happening, so it definitely isn't our fault if there is one, which is a win. But if it does sound, we have a dispersal policy at King's, so that means you just leave the building and move away from where the fire could be. If this happens after 5 o'clock, because of that dispersal policy, we will have to just finish the event early, which obviously is not what we're hoping for. But if it happens beforehand, we'll do our very best to kind of get everyone back in and restart. But hopefully, this will all be irrelevant. Okay, the last thing is we are being recorded. This is being live streamed, but it will be recorded so that if you want to watch it back or if you want to share it with other people that couldn't make it, that will be possible. So I'm going to have a little bit of an intro. So why are we celebrating John Frederick Daniell? So many of you may not know or have heard about him previously. So he was born in 1770, which obviously is some time ago. But he was really interested in understanding the world around him, which I think is something, as scientists, we can all identify with. But he was a bit of a generalist in terms of things that he wanted to understand and measure. So as part of his kind of study, he wanted to, and things he invented were a hydrometer, so to measure atmospheric humidity, as well as a water-based barometer, a pyrometer, so to measure things that are extremely hot, and also invented one of the first quite safe blowtorches. So again, quite a diverse range of instruments that he invented. But he was really interested in these new and upcoming fields of research at the time, and these included electricity, but with a view to doing electrochemistry. His friend at the time, Michael Faraday, was someone that really inspired him, and so he realized that the research he wanted to do, which was related to atmospheric chemistry, needed a reliable battery. So to facilitate that research interest, he developed the very first battery, the Daniell cell. Around the same time, King's College London, so where you are now, was founded, so in 1831, and he was appointed the first head of chemistry. He actually was a really passionate educator and gave up full-time research so that he could teach undergraduates here at King's. Unfortunately, around this time, he actually lost his research book, his notebook, which is pretty awkward because he actually lost all of his research, which is quite opposite, apparently, to his colleague Faraday, who was very rigorous in his record keeping. So he had to repeat all of his experiments to confirm what he'd seen previously. He was able to do so and publish that in 1834, but unfortunately this was the same time that his wife passed away, leaving him a single father of 7 children. So, despite all of this, he had a huge success in terms of the range of chemistry that he did, but in a very strange turn of events, he was at the Royal Society presenting some of his work to his peers, and he passed away at the age of 55, a day after his birthday. But due to the breadth and importance of the work that he'd done during his lifetime, he was awarded every single medal from the Royal Society, which is pretty, if you're going to do it, that's a pretty exciting thing to get out of it. So I wanted to acknowledge as well, so Dr. Stephen Robinson, who is with us today as a King's alumnus, and it's because of his drive to recognise John Frederick Daniell that we're even here today. So he started this as a lecture and has, looked after it for a very long time before handing it over to us to continue on. So yeah, thank you very much, Stephen, for doing so. But now, the people you've actually come to see. So I'm going to hand over now to Jhanelle. But thank you very much. Enjoy.
Hello, can you all hear me okay at the back? Great. So, hi everyone, I'm Jhanelle, and as was said, I'm a PhD student here in the chemistry department. I also did my undergraduate here, so I'm a little bit of the furniture, been here a moment. And today I'm going to talk to you about, I think this is quite catchy. I chose the title From Big Questions to Quantum Answers, which would imply I'm going to talk to you about big questions and quantum answers. And I'm not going to do that. I'm actually going to tell you a far more exciting story, and I'm going to tell you about how I came to own the 3 periodic tables I've owned throughout my life. And I think that will give you a little bit of an insight into how I ended up here talking to you today. So let's start with periodic table number 1. So I got this age 10, and there's a lot of context as to how I came to acquire this periodic table. And first of all, to understand how I came to get it, you need to know a few things about me. So I've been speaking long enough, and you've probably noticed that I'm not from the south of England. I am from a small town, actually. Well, second biggest town, but, compared to London, it's quite small. So I'm from a town just outside of Birmingham. And if you've ever read The Hunger Games, I would describe this as like the District 12 kind of vibe of the UK. And there wasn't a lot going on there, to be honest, when I was a kid. I won't lie to you. And I had a few passions at the time, and one of the big things I was interested in was chemistry. And I really like science, and that was because I inherited an encyclopedia when I think I was about 8 years old, and the first book was on atoms, and I just never let it go, right? And I thought it was a bit like the world was like Lego, this idea that everything around you could be made up from just a few bricks, just put in a different way, blew my mind when I was a kid. So my parents used to buy me loads of science books, and I used to get loads of science kits for Christmas. At school, I used to get an extra hard worksheet in science, and that was kind of the extent of my passion for science, because I didn't actually have anyone to share that passion with. I didn't know anyone who studied science, and to be fair, I actually didn't really know anyone who studied past the mandatory age, because that wasn't very common in my town. But that was okay. I was enjoying my life until age 10, the year of the periodic table. We go to Warwick University. To this day, I'm still not quite sure why they... We'll just keep going. I'm not quite sure why they decided to take a bunch of 10-year-olds to an actual research lab, but there we were. So they take us into this lab, and I met this PhD student who, to me, was the coolest person I'd ever met. So she had a lab coat, and she doodled all over it, which was insane. And she took me around all of the facilities. She showed us what was going on, kind of a bit of like what you've done today. And she painstakingly answered every question that I had, right, which were probably quite stupid. But she stood and paid attention to everything I had to say. And at the end of the day, she gifted me a periodic table. And on it, she wrote a note saying, "Keep asking questions and stay curious, Jhanelle." And that was the first periodic table that made it onto my wall. So from that moment, it was set. I was going to study chemistry, right? And everything was going well. I went to secondary school. I was in my rebel era, so I was kind of toying with physics, but I was going to be a chemist. And then the next big thing happened that would periodic table one. The next big thing happened that was kind of going to put a spanner in the works for me, and that was tuition fees. So I'm in secondary school, and they announced that they're going to raise tuition fees from $3,000 to $9,000. Now, looking back, that doesn't seem like that big of a deal, right? But you need to understand, to my town, this was catastrophic, because suddenly, overnight, university was a waste of time. There was no point going. You were going to get into loads of debt. You might as well just do an apprenticeship. And to be honest, unless you're going to do a real degree, right, there's not really any point in going, because you're not going to earn that much more after a degree. And also, when you think about it, in those 3 years you were gallivanting around in a library, you could have had like a real job and been a real adult and be contributing towards your family. And that's when the pressure started. So I'm sure we all know the family-certified real degrees, right? So this is when the pressure started, because for me, I was good at science, so why can't I just be a doctor? And if I didn't want to be a doctor, then I'm pretty sure you could be an engineer. So suddenly I had to be a doctor or an engineer, and that was kind of the vibe. And everybody kind of sat around and discussed how I could do and what options I could choose to be a really good doctor or a really good engineer. But there was something else kind of happening at the same time too. So I was doing quite well at school, actually, quite well. And there were murmurs going around that maybe I could do the impossible for my town. Maybe I could be an applicant to Oxbridge. Now, you need to understand that when I was writing this, I made a joke about how I think getting into Oxbridge was kind of like being a footballer and playing for the Premier League or getting into X Factor. And then I realized I actually know more people from my town who have been on X Factor and have played football in the Premier League than I do have gone to Oxbridge, right? So this is now the town is riding on me. And I realized that if I got into Cambridge, it didn't matter what degree I did, because going to Cambridge would trump, right, whatever degree. So if I wanted to study physics or chemistry, I was going to have to get into Cambridge. So this was the new dream, right? You girls going to Cambridge. So I'm taking this serious, right? I get myself into a selective college. I'm doing every extracurricular. I'm in every academic pursuit possible, right? Come the end of year 12, my personal statement has been written. My college has been selected. My course has been selected. My parents are already planning, right? The admissions party for when I get in. The balloons have been ordered. And it's all going really, really well. Until I get my AS results. Turns out I'm not very good at maths. So that was a hard hit for everyone involved. And I laugh about it now, but I really need you to understand that at that time, that was literally the worst thing that had ever happened to me, right? So to this day, I have only ever cried once in front of my friends, and that was when I opened that envelope on the college car park. And it felt like my life was over, right? I had like the weight of the world, in all honesty, it was Dudley and my family, but I had the weight of the world on my shoulders, and I just felt like I'd let everyone down. Right? I didn't really know what I was going to do, because the thing about failing maths, also, correction, 10 years later, I actually didn't fail. I just didn't do that well. It was not a fail, and even still, 10 years later, I still think that I failed. I didn't. But you can't be an engineer and suck at maths. And it's also quite hard to get into medicine if you suck at maths, and that was kind of what you'd put all of your eggs into. So I didn't really know what to do. 10 years later, sometimes I think, I don't know if I failed that exam on purpose, because looking back now, that was one of the best things that I think could have happened to me, because for the first time, everyone sat down and they asked me what I wanted to do, right? And now all the options were off the table that everybody had chosen for me. I got to think about, what is it that I actually want to do? And there's a big chunk of this story that I've missed out. So obviously I'm standing here in King's, and I said I went to King's. So while I was riding that Cambridge wave, I did also have to have, other options. UCAS requires 2 options, or you have to apply to 5. So I'd visited other unis, and one of my first trips to London was actually to the King's Open Day. And when you meet someone or you go a place and you just have that vibe that like it was just meant to be, right? So I came to King's for the first time, and first of all, saw black people that weren't directly related to me, so that was a hoot, not seeing that before. I also got to see all of these students who just genuinely seemed like they enjoyed what they were doing, and nobody was holding them at gunpoint under duress in the class. And it felt like there was just this history and this vibe, and everyone was just so nice, and I felt like that was the place that I wanted to go. So when I was asked where did I want to go, the natural answer was King's, right? And I'd fallen in love with London along the way, so that was the perfect choice for me. When it came to subjects, it all kind of started with chemistry for me. And the thing is, I really do like science, and I think chemistry is a little bit like the switchboard, where it's like a melting pot, where all of the sciences come together, right? And they just kind of melt into this one subject, and then we turn it into something really cool to solve actual real-life problems in a fun, kind of creative way. So I felt like the obvious answer for me was chemistry. So a year and a half later, I buckled down for a start. I resat what I needed to resit. I filled out all my UCAS. A year later, I moved into my first flat in London. And I took that periodic table from Warwick and I put it on my wall, right? And that was kind of a sign to me, like, girl, you did it. The periodic table then pretty much fell immediately off the wall, and it slid between a crack between the bed and the wall, never to be seen again. So if anybody does apply to King's and you're in Stratford 1, if you find a periodic table in flat 003, room C, that would be mine. But it was okay, because 2 days later, I started my induction at King's. And they gifted me a new periodic table. So that was the periodic table that went onto my wall next. And it went onto the wall, like with every student, with a few other things, right? There were Polaroids of me and my friends living up life. There were my fairy lights. There was all my new stationery, because I was living my best life, right? I had all my new stationery. I was in every lecture with my new highlighters. I was out at every social with my friends, and I was having the best time, except I wasn't. I was struggling, right? I was struggling. And I had been so excited to come to King's, but when I got here, first of all, small disclaimer. I said I love chemistry, but I didn't actually have a lot of practical experience. So when I was at school, there was this guy called Michael who decided to precipitate out the entire stock solution for the entire school of silver nitrate to see if he could make enough silver to sell on the market. So then we subsequently got banned from doing all experiments. So I hadn't actually really been in a lab. And don't get me wrong, the lecturers were great, and I got so much help, but I couldn't shake this feeling that if I went and took the help, I was failing this imaginary test. And it seemed like everybody that I met just knew stuff, right? They knew each other, they knew each other's schools, they knew each other's towns. I didn't know anything. So I just decided I was going to take a little bit of a backseat because I felt a bit like an imposter, right? And the one thing I was going to do is not be caught out. So this was kind of the approach I decided, like, I'll just keep my head down. It's only 3 years, and I can go back home. Everyone will be like, woo, she did it. And we'll just, we'll pretend that whole thing didn't happen. And obviously, I know Dr. Isaacs is an organic chemist, so I'm sorry for what I'm about to say, but organic chemistry is not for me, right? It's not for me. So we have an exam coming up, and I know I'm going to fail. And I don't mean fail like in, I failed my AS. I mean like fail, like I'm going to be escorted off the campus fail. And I'm trying everything, right? So I'm watching every YouTube video. I'm doing every text. I'm trying everything, and it's just not sticking. And I come to this realization I'm going to have to bite the bullet because I've got two options here. On one hand, my lecturer might look at me with a face of disgust, right, and disappointment. But that can't be worse than my parents' face when, like, in a few months, I arrive back on their doorstep and have to explain that 9,000 isn't really that much money if you think about it. So I decided I was going to go and ask them for help. So at the end of the lecture, I'm loitering around. I see her at the end, and there's a few other students around her. So I go down, and I hear the other students are also asking her for help. So she organizes a study group for us. She invites us back to her office. She has a whiteboard and pen waiting, and she starts off with, there's no such thing as a stupid question, right? And 1 hour later, I leave the room being like, first of all, I can understand why people would study organic chemistry, like it's not so bad. Second of all, I'm an idiot. And not because I didn't understand organic chemistry, but because I have been suffering this entire time. And it turns out that, first of all, nobody else was getting it. And also, I could have just asked. And I realized that just because the most intimidating were the loudest didn't mean that they were the majority. So the girls that I met at that room, we started studying together, and I started meeting loads of other people. And suddenly I was in that King's that I visited that day. And I felt like that was when uni really started to take off for me. However, I was enjoying chemistry, and I was enjoying the course. But it wasn't really giving what needed to be gave. I had this whole dream, right, that I was going to be this researcher, that I was going to dedicate my life to answering these really cool big questions, and I was going to do it just for curiosity's sake. But there wasn't really anything that was screaming out to me. There wasn't really anything that was giving me that moment. And organic chemistry was okay once I knew what an electrophile was. I still don't 100% understand how to fill a d orbital, so I don't think inorganic chemistry is for me. And I genuinely don't know most of the laws to thermodynamics. I was going to say how many, and off the top of my head, I couldn't tell you. So, and me in a lab is I don't know if you've ever seen like those clips of chefs running back and forth in a kitchen. That is live footage of me in a wet lab. So I was kind of thinking after 3 years, I'm ready to check out. And one night, in my sad girl hours, I decided to resign myself to just getting a job in banking, which is what my parents had really always wanted. And I took the periodic table down off my wall and put it in the bin because I thought chemistry was done for me. And then in my 3rd year, I had a lecture from this guy called Isma, who was this kind of elusive lecturer who had just arrived and kind of tumbled in and gave what I would still consider to be one of the best lectures that I ever had. Or have ever seen, to be honest, even now into my career. And he sold me this whole story about how there's this whole nano world, right, that exists right beyond our eyes, that we can't see, that breaks all the rules, doesn't have any rules, yet explains all of our rules somehow. And suddenly I was like, this was what I was looking for, this is that moment. And next thing I know, the whole plan diverted. I applied for his summer project. I went into the lab against all of my wishes. I actually kind of enjoyed it, so I swapped over to the master's program. I joined his group to carry on my research project. And next thing I know, I'd applied for a PhD program. And here I am. And with my first stipend, with my first wage as a PhD student, I went out and I bought myself a new periodic table. And I hung that on the wall because that was what I'd done 4 years before when I started studying. I kind of wanted to keep the tradition going, right? So I got myself quite a jazzy one, actually, from the Science Museum. And people ask me a lot about what changed. And to be honest, I don't really think anything did. I think that I'd always enjoyed chemistry. Like I've said, I'd always known that I'd enjoyed chemistry. But I think I kind of lost sight of what the point of university was. And I think as students at whatever stage you are, I think we can all relate to one thing as students, is that like education is a bit like cleaning. It's really fun until you're asked to do it. And I think it's really difficult to remember why you're doing something. I kind of felt like I was doing a degree to get good grades, and chemistry was something that I had to do to get good grades so I could get a good job, and I forgot that I actually chose it because I enjoyed it. And my research now is, so I work in ISMA's group, and I look at how electrons tunnel or how they move through proteins. So we can understand how to put them into nanocircuits to use as biosensors or just to make tiny little, I don't know, biophones out of little proteins in your body. And I couldn't be more happy with it. And I think that if I had some advice for me when I was younger, my first thing would be just calm down. It's never that deep, right? I think it's really funny that along this way, I've spoken about what were some of the worst moments of my life or things that I thought were going to ruin my future. And it's really funny to think that I thought my future had been ruined before it even began. Like, I was 16, like, girl, come on. You've got a lot more things to go through before you get to that point. And don't get me wrong, like, failing that maths A-level felt like the worst thing ever, right? But when I look at it realistically, as you grow older, you have a lot of paths in front of you, and there aren't really any right or wrong ones necessarily. They're just different paths that have different outcomes. And if I have one piece of advice to me, it would be to just choose something that you enjoy, because unfortunately, they're going to be hard and you are going to struggle and sometimes you're going to fail, but it's a lot easier to take that punch if you at least enjoy it, because at least then it would have been worth it. So, yeah. That's everything from me. I think that's a good note to end on. Do I have questions? Do I have time for questions? No, so there's no, just ignore this slide. There's no questions. But thank you so much.
Can I put? Oh, that's good. There we go. Hi everyone. Thank you all for having me here. This is my first visit to London, by the way. So it's been wonderful. Yesterday was so beautiful, and then today happened, and I was like, oh, I'm now in London, the London that I heard about. Thanks for having me. My name is André Isaacs. I'm a professor at the College of the Holy Cross in Worcester, Massachusetts. Some people in other places of America say Worcester, and we quickly remind them that it's Worcester. It's my pleasure to be here. So I'm going to start off by telling you a little bit about myself and how I came to be a chemist, and hopefully will inspire you all to think about chemistry or anything related subjects for your future careers. So where did I start? Okay, so I grew up actually in Kingston, Jamaica. Anybody ever heard? I cannot run. No, I can't. Actually, I did try to do track when I was in high school, but in Jamaica, there's a very high bar for you to be a track athlete, and I did not meet that bar. So I went to high school in Kingston, Jamaica, and I always wanted to do something in science. Actually, I didn't want to do something in science. My grandfather wanted me to do something in science. And that's because, as Jhanelle said, everybody wants their kid to be a doctor, a lawyer, or in Jamaica it was just a doctor, a lawyer. Anything else, you were useless. And so my grandfather always wanted a doctor in the family. Somebody had to be a doctor. None of his kids wanted to be a doctor. He's got his youngest son to enroll in medical school. And after 2 years, he decided, I just want to be a teacher. So then, of course, that meant the grandkids had to be a doctor. And of course, it fell on my shoulders that I needed to be the doctor, and I was like, we'll see. So I did really well in math in high school, really well. Biology, okay. Physics, Slade. Chemistry, the worst. The worst. Chemistry was terrible for me. I hope my high school teacher isn't listening, but I did not love that class. And I really, really struggled with with chemistry in high school. It just didn't click for me. For some reason, I wasn't getting how to balance equations. Anybody really good at balancing equations here? Yeah? Raise your hand. It's all good. You can flex. It's all good, yeah? All right. So balancing equations, I did not get it. I could not get why iron was 2 here and 3 there, okay? It didn't make sense to me. And so my mother said, why don't you go talk to your uncle? Like, he was in med school. He's now a teacher. He will help you. So I went and I talked to him like, can I get some help with this chemistry thing? And he said, okay, why don't you come to my evening school? He ran an after-school program for continuing education for adults. So I went, and there were all these adults and little me. And honestly, it was the best thing I ever did because he explained it so well. And this is going to be important later as I talk about mentorship, was you really want to find people who can mentor you in a way that's useful to you. My uncle was very good at explaining chemistry in the weirdest but coolest ways. Very strange, but it made sense. Like, for example, when I was learning about oxidation, anybody remember learning about oxidation? Alcohols go to carboxylic acids, right? So I was like, how am I going to remember that? Alcohols, carboxylic acid. And he's like, just think about Jesus. I'm like, what does that have to do with alcohols and carboxylic acids? He's like, remember, they gave Jesus vinegar on the cross. He was like, I don't think they gave Jesus vinegar. They just gave him some old alcohol that was in the corner, and it oxidized to vinegar. I was like, okay, all right, okay, that makes sense. And so that's how I remembered in high school that alcohols go to carboxylic acids. And he has some very funny, weird ways to connect things to religion, to sports, and that made sense. And that's how I learned chemistry and actually ended up doing pretty well in chemistry in high school. At the end of high school, unfortunately, I applied to college in Jamaica. And I got into the University of West Indies, yeah. I was all set to go to college, and unfortunately, there was a tragic event. My uncle passed away, and we're not there yet. And I had a whole breakdown. You have someone you look up to, someone who's guiding you, someone who's supporting you, who you were hoping would like hold your hand as you do all this stuff that you're excited to do, and then the next minute they were gone. And so I decided to postpone my college acceptance, and I waited. I was like, I'm not going to go to college here. I deferred it. And during my year, after deferring it, I decided, you know what, I just want to leave Jamaica. I was upset about, like, his passing. And so I applied to colleges in the U.S. And I decided I was going to apply to Jesuit colleges, Jesuit Catholic colleges, because I went to a Jesuit high school in Jamaica. So like, at least if I go to the U.S., the school will be familiar, right, similar. And so I applied, I got in, and I left. And I went to the College of the Holy Cross in Worcester, Massachusetts. You've seen it, you've heard about it before, right? So I'm actually working where I went to school. And I had a blast. It's really crazy. I fell in love with chemistry immediately. And I was thinking of doing math as a major. But chemistry, I bodied that. Like, first semester, it was just balancing. I was like, yeah, my uncle taught me that. Everything just made sense. And it was really him that really helped me get there, right? So I did really well in chemistry in college. I took organic chemistry my next semester, fell in love with organic chemistry, and I'm going to teach you all some organic chemistry today, by the way. So hands of those who like organic chemistry. Hands of those who hate it. After today, you will love organic chemistry. You too, Jhanelle. And so I fell in love with it. And, I didn't have a lot of belief in myself still. Like, I grew up in Jamaica. Nobody, did anything after, nobody really no one in my family went to college, right? Most people had a high school. My father did, but he got a master's in math. And nobody else did much after that. So for me, this was already new territory. And then I thought I was just going to finish my college degree, go back to Jamaica, make some cement blocks, and, call it a day. And then my college professor was like, are you going to go do a PhD? I was like, a PhD? Me? A PhD? He's like, yeah, you're like so good at this thing. You should do it. I was like, okay. So I applied. I did some research in my undergraduate institution, really fell in love with research, and then committed myself to 5.5 more years of doing research at the University of Pennsylvania in Philadelphia. That was an amazing first few years for me. I really loved it, did really well in my classes my first year. And then I had a life crisis in my third year. I ditched my then girlfriend, and I had an awakening, and then and then I found myself, and I came out as a queer black man, and then a lot of people in my family kind of just rejected me. It was a very hard time in my life. I thought about quitting grad school. I had no friends. I lost a lot of friends. Jamaica's a tough country to grow up in, fairly homophobic country. And so I really struggled. And so I decided I was going to quit. And then my PhD advisor was like, how about we send you on a little vacation to San Francisco? And so he's like, we have a collaborator there. Go work in San Francisco at this company called Genentech. Go enjoy life. Come back in 2 months. So I went, really loved the city, got a break from life, from work, learned a lot of stuff, did some solid phase peptide synthesis, came back, and we published a bunch of papers after that. It was great. And then I went back to California to do my postdoctoral work at, oops, did I click something? Here we go. I went back to California. I loved it so much, did my postdoctoral work at UC Berkeley. And I worked on some synthesis projects and with Professor Richmond Sarpong. And then while I was there, I saw that my college was hiring for a professor, right? And I was like, oh my God, I have to go back. So I applied and I got the job. And so I went back to Worcester, Massachusetts, and started my job there in 2012. And then I was promoted to associate professor with tenure several years later. So that's kind of my trajectory, how I got there. It wasn't without pitfalls. You will have a lot of challenges, but the whole point for me, and I'll talk a little about this later, is that mentorship is really important. So my advice to you, first piece of advice today, is to find someone who you can trust and you can talk to. And as you hear from Jhanelle, professors are always willing to help. You just need to talk to them. And it doesn't have to be a professor. It could be a family member. It could be someone you look up to. It could be me. Send me an email. We can chat. All right, so let me tell you about what I'm gonna, yes, this is the chemistry part of the lecture. Welcome. So get your thinking caps on. And so what I'm going to do here, Jhanelle, you ready? Get your notepad out. Is I'm going to reintroduce you to some organic chemistry. And I'm going to tell you about the chemistry that I do, and you're going to leave here as professionals, all right? That's the goal. And then I'll walk you through some click chemistry. Anybody heard of click chemistry? Yeah, perfect. And then I'll tell you about how we use it and how we make heterocycles. I won't dwell, I don't expect you to remember a whole lot, but as much as you can. And finally, I'll tell you why I'm excited to be a chemist nowadays and how I think we can, as a society, inspire you all to become scientists and how we can broaden participation. Okay, Lewis structures review. All right, class. So, who remembers how many bonds carbon makes? This was supposed to be like an animation, but it's all here. So carbon makes 4 bonds. We all know that. Here is our periodic table, and you can tell from here, carbon makes 4 bonds, nitrogen makes 3, oxygen makes 2, and fluorine makes 1 in its neutral state. Do we all have that? Yes, and we all remember that? Very nice. I see nodding heads. I love that. All right, and so we can use that information, right? And for any non-chemists or scientists in the room? Yes, 2, 3, great. You're going to learn some chemistry today. So how we draw Lewis structures, really, to draw the things in their neutral state, really is to follow these rules. If you follow these rules, you can literally connect everything together, right? So if carbon makes 4 bonds, you can just draw 4 bonds off of carbon. And if you have 2 carbons, you can connect 2 carbons together. Just make sure they're still making 4 bonds, 1 to each other, right? And now you have 6 open spaces, right? And with those 6 open spaces, you can tack on an oxygen, but oxygen needs to make 2 bonds. You got another bond, and then the space is left for all the other 6 hydrogens, right? Lovely. Doesn't always work out that way, especially if it's charged, right? But if it's neutral, then you can do this pretty quickly, and this is why I love organic chemistry, right? So we really focus on mainly these atoms, follow these rules, and then we can draw Lewis structures. Here is acetic acid. It's a little bit different. You'd have to calculate your double bond equivalence to know that there's a double bond there. But if you follow the rules, you'll end up with the same number of connections, right, that these atoms should make, and this is acetic acid. Anybody can tell me where you find acetic acid in your homes? There is some probably under your sink, probably in your cabinet. Anybody? I mentioned the name earlier. Vinegar, right? That's the stuff they gave Christ. So there it is, ethanol to acetic acid. That's the oxidation that I was talking about earlier. That's an oxidation. I will give you that. Okay? So we're good on our Lewis structures so far? Yes, it's all coming back. Everybody who hasn't seen it for a while, fantastic. Now we're going to go into line angle because as organic chemists, we're very lazy or we're very practical, right? Imagine if you have a molecule with 100 carbons. I'm not going to write C 100 times, right? I don't have time for all of that. So what do? We have a nice little line angle way of representing this, yes, where instead of writing carbon, what we do is every point represents a carbon atom, right? And every time it bends, that's a new carbon atom, yeah? Anybody seen line angle? Hands up those. This is a class. Hands of those who've seen line angle. Ah, all right. So does it make sense for those who haven't seen it? Yes, that every time the line bends, this is a carbon. And I have it color-coded for you here. Those are all carbons, right? And every time it bends, it's a new carbon. So that's a quick way to draw it. And then you might be asking, where are the hydrogens, right? Yeah? The hydrogens are implied. And they're implied, which means if I don't draw them there, and carbon makes how many bonds? 4. So if I don't see a hydrogen, I assume that however many connections are not drawn, that many connections to hydrogen exists. So this carbon is making how many connections? 1 currently, visually, right? So how many? It must also be connected to 3 hydrogens. This carbon is making how many connections visibly? 2. So it must be connected to 2 hydrogens. That's it. And now if it's not a carbon atom and it's like an oxygen, then we just write the hydrogen, right? There has to be some weird thing. So this is acetic acid, same thing. Here's the carbon, other carbon connected to oxygen, connected to that. And this is why we have to do that, okay? We have this molecule called resveratrol. How many carbons are in this molecule? I see some counting. Can anybody count this quickly? Any volunteers? Yes. 14. Oh, see, he counts really quickly, right? Do we see that? There they all are. There are 14 carbons in this molecule. And now you see why we draw it like this, right? Because it's just a lot easier to do this. So now we're experts at Lewis structures. Everybody follows along. So if I draw a molecule for my research, you'll understand how many carbons are in it. Yes? All right. Great. So let's talk about my research. So my lab, we're very much interested in making heterocycles, all right? And what are heterocycles? Heterocycles are these ring compounds, basically, and they have like non-carbon atoms also present in those rings. So you can see this ring has 4 carbons and an oxygen, right? This ring has 4 carbons and a nitrogen. These are called heterocycles. And why do I want to make these molecules? Well, the data is here, right? Over 50% of known organic compounds that exist in nature have heterocycles present in them. So they're very important systems to recognize and know how to make. But if you look further, over 80% of active pharmaceutical drugs, some that you all take, for all your different, ailments, ADHD plus, has heterocycles present in them. And so we really have to come up with really neat ways to make them. So my lab, we really want to figure out how to make these systems. And the ones we want to make specifically are the ones that have nitrogen atoms in them. So here are some that have nitrogen atoms in them. Anybody recognize some of these? Yeah, we have nicotine, right? You can see that's 2 rings with nitrogen in there. We have quinine. By the way, quinine is in your tonic water. So if you ever have a gin and tonic, which none of you should know even exists, you would find some quinine in your tonic water. Caffeine, which I drink like loads of that daily. You can see those nitrogen atoms in that ring. This anti-ulcerant, and also these antipsychotic drugs like Abilify or Seroquel. These all have ring systems in them. Are we feeling like heterocycle experts now? You can recognize heterocycles? Yes? All right. I told you, you're going to have class today. All right. But if you don't believe me why these are so important, I want to show you last year's, the US FDA approved drugs. There were 36 drugs that were approved by the FDA, right, for use in humans, and 19 of them are small molecule drugs, molecules that we can make. And if you look at these, if you look closely, you can see, do you see heterocycles in these rings, in these molecules? Here's a heterocycle, here's another one. This one has 3, right? This molecule has 1 here. Everybody's following along? You can see literally all these ring systems, most of them have heterocycles in them, right? So this might be more than 80% on this slide alone, right, of these active pharmaceuticals. So my lab, we see this, and a lot of other labs are interested, and we see this, and we're like, these ring systems are so important, we want to come up with new ways for making them, right, so that a pharmaceutical company can make them more efficiently. And so that's been like our goal, and this is the rest of the compounds. So how are we going to do that? Right? So the way we chose to do that is to use this really powerful reaction called click chemistry. And click chemistry is really, I see some nodding heads, yeah? Click chemistry is really a concept. I like to tell students that. It's not a particular reaction, and I'll explain why. It's really a concept, and it's been defined by a lot of people. A click reaction is any reaction that's just, simply put, really efficient, right? You can like fuse molecules together in a very, very efficient way, and they come together. And so people have defined it, right? So if you get high yields, if you get simple reaction conditions, if you can do it in water and it tolerates oxygen, and you can isolate the product simply. Basically, the most perfect reaction. You just dump and stir, walk away, filter, and boom, 100% yield, right? So that's a click reaction. And other people have defined it a little bit more narrowly. They're like, well, in addition to that, you must make carbon bonds to like nitrogens and oxygens, right? If you do that, then it's also click. And so we were excited to use click chemistry. And so this is the original reaction that we call the click reaction. And it's not really yet, and I'll explain why. So this reaction, you can see, these are 2 carbon atoms here. They're really just joining up. Just look at the picture in the middle. They're really just joining up with those 3 nitrogen atoms, okay? And you take the 2 carbons and they join up in what we call a concerted pericyclic reaction, and they form this beautiful 5-membered ring. So do we see how they just join up together? And that's what you get. So these 2 atoms join up with these 3 atoms, and you get a 5-atom ring system. And this works really, 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 really well, and reliably well. And the reason why people are fascinated with this is because this ring structure is really cool, right? And we'll talk about how cool it is. But this happened in like the late 1800s and the early 1900s, but there was a problem with it before the current technology. And the problem is, it kind of sucks. And this is why it sucks. If you draw these 2 atoms, you can imagine flipping it in 2 different directions, right? You see that? And I've drawn them here for you, right? You see that? You can turn it that way or that way. And if you do that, you can get 2 different products, right? We call those regioisomers, right? They're differently oriented to the A side. Everybody follows that? Does that make sense? And that kind of sucks. If you only want to make one of them, well, what are you going to do with the other one? And the problem is, if you do this, you typically get around 50-50 of both. So nobody really ever used this in a pharmaceutical industry, because if you want to sell a drug, you want to be able to make it efficiently, right? You can't like cook a pot of food and throw away half of it, right? You want to use all of it. And so nobody ever really used this reaction as is, because it just was really bad. And the other thing is, you have to like really use high temperatures. And that's when, well, not that's when, later on, since in 2002, that's when this came about. This is the click reaction now. So the quote-unquote click reaction is making that reaction I just showed you very, very efficient. And what people found is that if you use copper as a catalyst, you can actually make this work really, really, really well. Not only can you make it work really well, but you only make one of the two possible outcomes that you desired. And the copper atom facilitates that process. And this is the outcome. You get quantitative yields like 95, 100%. You get like increased rates, and you can do the reaction in water sometimes, and you can filter it. So this is considered the premier click reaction, and we call it click chemistry because there kind of is no other reaction that's as good as this one right now, and so we just call it click chemistry. All right, hands up those who learned something new today. I'm curious. Hands up those who think this is cool chemistry. I agree. And you know who else agrees? A lot of other scientists. And why do they agree? This is what they do with it now. They do polymer chemistry. They make materials with it. They have the structure in agricultural stuff. And there is even a new field of chemistry that was developed called bioorthogonal chemistry. And anyone heard of bioorthogonal chemistry? Okay, I'm going to explain it to you. So bioorthogonal chemistry is really a way to do chemistry orthogonal, or at the same time that biological processes are happening without disrupting it. So basically, you can do chemistry in a living system, in a cell, without impacting the biological processes. It's pretty cool. And so what Caroline Bertozzi did was she showed that you could take like a protein or an enzyme or whatever, and you could put like an azide on it, that's the 3 nitrogens, and then you could take a fluorescent tag, something that lights up, and you could put the alkyne on it, and then you can put it in the body or in the system, and they would click together, and then you could study what happens to the protein. And you could see the fluorescence. Isn't that cool? So that's kind of a neat way to apply it. And this took off because it wouldn't impact the biological processes, but you could study what's happening. And so this really took off. And it won the Nobel Prize last year. This chemistry, after 20 years, was awarded the Nobel Prize. So Caroline Bertozzi, who applied it to the living systems, as well as the 2 guys who developed the copper version of it, 3 of them together won the Nobel Prize because this chemistry, everyone's using it now to make these ring systems. So that's the background of this chemistry. And then I tell you all of this to tell you that we actually don't care about this chemistry. we care about it, but we don't care about the product of this chemistry. What we care about is breaking it up. And what we do is we make it and then we break it. And I'm not going to belabor this, but this is kind of what we do. We can take the alkyne that I just showed you, we can click it together with the azide to give you the triazole, and then we can manipulate it into something else, right? And that chemistry is complex. We're not going to go too deep into that, but that's what we do. We like kind of hijack the click chemistry. Does that make sense? We take it, we hijack it, and we break it down, and then we use this to make other nitrogen ring systems. So that's kind of what we do. And I'll just show you in a few quick slides, and I'm going to switch to some other stuff about how we use it. So this is kind of how other people have used it. What you get is what we call a ketenamine after you break it up. So if you look back, what we're doing is we're losing these 2 nitrogens. Everybody see these 2 nitrogens? We're losing them, and we're keeping this one. And there it is. That one's here. And then you still have the 2 carbons. Okay? So that's what's happening. You're literally losing nitrogen gas. And so now we can use this, and we can react it with other things and make new systems. And so what have we been using it for? This is what we've been using it for. And I'll transition quickly to that. So we've used it to make all of these heterocycles, new heterocycles. We have this is an ongoing project. I'll talk about this one in more detail. We're trying to make beta-lactams with this chemistry. We're also making these dihydroisoquinolines with this chemistry. And you notice all of these are ring systems with nitrogen in them, right? They're the products, so that's our goal, right, to make those ring systems. And so here are some of them that are actually kind of cool, why we like them. For example, this ring system is highlighted in red. Do you see that? That one is really neat. They have really high fluorescent properties. And you can use them. Actually, there's this group in Japan that's studying them for like their OLED properties, to put them in like TVs. And then here is this really neat system. This is an anticonvulsant. And this one actually has some really good properties as an HIV-1 integrase inhibitor, right? And then finally, this is a beta-lactam, which I'll talk to you about shortly. So you can see these ring systems have biological activity, right, and use. And so we really want to use this chemistry to make them. So I'll talk to you quickly about how we go about this. So for those of you who want to imagine what it's like working in a lab like ours, what we call or research is methodology, right? So as organic chemists, you can do methodology, or you can do synthesis. Synthesis is kind of like, here's a molecule that nature made. I want to make this molecule exactly how nature made, the molecule that nature made. Or methodology is where you develop your own reactions to make a system that exists already. And so we are on the methodology side, where we're making, developing chemistry to make ring systems that are already exist. And so this is one of our chemistry, and I just want to show you what we do. So what we do in methodology, or in our lab, is we have to analyze all the variables, right? So for example, what are the parts that you need, right? The reagents that you need to make this chemistry happen. So for our chemistry, we need a copper source, right? So I told you this reaction is catalyzed by copper, right? We need a copper. We need a base. In our case, for this particular reaction, we need oxygen. We also need some solvent, right? You have to run your reaction in some solvent, yes? And then you have to run it at a particular temperature, right? And you have to run it for a particular amount of time. So there's a lot of variables. So when you're trying to find the best combination of all these variables, guess what you have to do? You have to explore all of them, right? So this is a representative table, by the way. So what you do is, say you have a list of 20 coppers, right? Whatever you can afford. And then you have a list of like 20 bases. And then you have a list of like 20 solvents. You take them one by one, right? And you put them together with a particular temperature, and you see what yield you get, right? And whichever combination gives you the best yield or outcome, percentage-wise, then that's the one you want to keep, right? And so what we did is we did that. And so my students do that a lot. So if you work in a lab and you do methodology, this is what you would do. You would go in the lab and you would set up the same reaction. You would change one thing, see what the outcome is, change another thing, see what the outcome is, and then you just do that until you stumble on the best outcome, right? And then once you get that, you make a big table and you show that it works with a range of things. And you're like, I figured out the best conditions. It actually turned out for ours that the first molecule we make was the best yield, but that's okay. All right, so I want to talk to you about the chemistry, the beta-lactam chemistry. And this beta-lactams are really, really cool systems, right? They look very simple, right? Now that you know your lowest structures, you know that. This is 4 atoms, right? 3 carbons and 1 nitrogen. How many hydrogens are attached to this carbon? I heard it? 2. Wow, you guys are quick. All right, so there are 2 hydrogens attached to this carbon. How many attached to that one? To this carbon. 2 as well. Nice, very nice. Okay, so this is a beta-lactam, a 4-membered ring system, all right? And this is a very important ring system. It looks simple, right? Just 4 atoms in a ring, right? But it's a very powerful ring system. And why is it powerful? It is the core structure of several antibiotics, a whole class of antibiotics. We call them the beta-lactam antibiotics. And they operate by inhibiting cell wall synthesis. And this is a beautiful list of some beta-lactams. You all probably have heard of this one, right? Penicillin, yes, everybody? Anybody has had a penicillin shot before? And so this is a 4-membered ring, and you can see that all of them have 4-membered rings. But what's the problem with antibiotics? Anybody knows what's our current problem with or issue? Resistance, right? So that's become a really big issue. And antimicrobial resistance is really killing us. Not even joking, like literally. You know, we need more solutions to the problem of antimicrobial resistance. And people have come up with a lot of ways for doing it. We're not going to go into the biology of it all. But the point is, one way to do it is to expose bacteria to compounds they haven't seen before, right? That they haven't developed resistance towards. And so over the decades, people have designed new compounds that bacteria haven't developed resistance to and have treated them as such. And this is actually a really new subclass of the beta-lactams. And the difference is there is a double bond in this position. And that makes it have different properties. And so we saw that and we were like, I think we can use this copper chemistry to make this. So that became our goal. And this is our contribution to this field. And this is a really neat compound. And so these are two of my students who worked on it. Unfortunately, I couldn't get them to do a chemistry PhD. He's now in medical school and she's applying. Yeah, they all go to medical school. It's fine. I'm not bitter about it. Maybe a little bit. And so this is kind of how we do it. I'm not going to rush you, walk you terribly through it, but you can see that we make this ketenemine intermediate, and then it comes together to give us the four-membered ring. Do you see that four-membered ring? That's very similar to the beta-lactams. So this is what we planned on doing. Now, as a chemist, you can always write on a piece of paper what you think should happen, right? But the proof is in the pudding, right? If you don't try it, it might not work. Anything can be written on a piece of paper and say, I think this atom is going to react with this atom in this way, and it's going to react with that atom, and I'm going to get this product. And then you go in the lab and you try it, and guess what? It doesn't work. So we went to the lab and we tried it, and guess what? It worked. Guess what the yield was? Guess what percentage we were getting? I want some guesses. What percentage do you think we were getting? 70? Anybody else? 92. Wow, you guys are hopeful. Maybe go in the other direction. Anybody else? One more guess. 3. Yes. Oh my God! Literally, that was a yield. We got a 3% yield on this reaction. 3%. And my students were like, they're like, no, bro, we're not doing this chemistry. This sucks. And I was like, oh my God, can somebody just try it? We can optimize it. Just change the copper, change the base. They're like, oh, from 3%, it's going to take a while to get that up to like something reasonable. So I was like, all right, guys, just somebody tries it. And finally, Gordon was like, I'll do it. And so he worked on it for a long time. And finally, we got it up to like 61%, right? After a long time. And what we did is we changed the base. We changed the solvent. We changed so much stuff, right? And it took him so long. And what we realized was that the copper, that really was what was important. Like, if you change, the copper was the main thing that impacted the yield. So we're like, okay, we need to find some money so we can buy some expensive coppers so we can try this. But then we found this, we liked it, and then we got a beautiful crystal structure. We got an X-ray crystal structure to show that we made it. This is actually literally a cool technique that you can use to literally see your molecule in 3D to prove that you made it. And so this is that molecule in 3D. And so we started making a nice little table to show that it works really cool. And then we started getting some low yields. And we're like, 30% is not so hot, it's not so cute, right? So like, is there anything we can do to make it better? And guess what, you all? If you go into science, the future of science is changing. Bench chemistry is no longer going to be the same because computational chemistry and technology and machine learning, that's going to be where it's at. So we were lucky to be invited to join this really big center for the National Science Foundation. And this center is this $20 million center funded by the National Science Foundation. And the goal of the center, the reason why it was funded, was literally to develop computational techniques to do organic chemistry. Like, can you fuse machine learning, data science? Can you take all of that and inform chemistry, right? So that's a big ask. And so to do that, all these amazing professors from all these really awesome institutions joined up together to answer that call, right? And so we have scientists who are like computational scientists, scientists who do chemistry and machine learning, people who are like amazing data scientists meeting up with organic chemists, and none of us know what each other does or understand. Or like, okay, can you fix this problem for me? Can you like come up with an algorithm that would tell me how to do this? And those conversations happen. And we're lucky enough to join this and get to use some of these new tools that were being developed. And I want to tell you about one that's revolutionizing, I would say, chemistry. For those who are thinking of, anyone interested in computer science in here? Yeah, so if you're interested in like chemistry, biology, and computer science, literally people are going to be working at this intersection going forward. And so what's happening is in Professor Abby Doyle's lab at UCLA, they developed this really cool program called EDBO+. It's an algorithm. And it's really just this extreme mathematical calculation where I showed you all my variables, right? You have your copper variables, you have your base variables, you have your temperature variables, right? And what you can do with this algorithm is you can literally just set up the matrix, right? Because if you think about it, when we do optimization, do you think we run all the combinations? Do you think we have time to run all the combinations? Let's do a quick combination. If I have 10 bases, 10 coppers, and 10 solvents, how many possible combinations is that? How many? Let's see the math come out here. 1,000, right? Do you think you can run 1,000 reactions? How long do you think that would take you? A long time, right? And so the problem is the way we do it, though, is we kind of cheat. We take all of the coppers, for example, we run all of them, and we pick one or two that gives us the best outcome. Does that make sense? And then we take that one forward. We combine just those two with our bases, and then we see which combination gives us the best, and then we keep moving. But you can probably see the problem with that, right? The problem with that is you never really test two that don't work together well, right? So you're kind of losing this potential synergistic effects between one you didn't try and another one. So you might be missing the whole thing. But we also don't have time to run them all. So that's where computation is amazing. So what you do is you set up your matrix and you run a few of them, right? You run a few combinations, you spit it into the algorithm, and the algorithm says, I think you should combine these four. I think based on your results, these combinations might be what you want. And then you run those combinations, and it learns. And it's like, actually, I think you should try these. And doing that, you actually get to the best combination much faster than if you did it on your own. And people have independently proven that. Like, they've gone back to reactions they've developed and used the computational approach and actually came up with different combinations that they never tried. And so this is kind of revolutionizing that. So we're like, yes. So every chemistry we go forward, we're going to use these computational tools to do that. And so what we did is we actually did this, and this is now where we're at with the computer-guided work. So it worked for us, and so we were able to like build this big table. And in black are what our numbers were before the computational work. And in blue, that's where numbers are now. And the ones that don't have a black, we just never made those before. These are new. But you can see across the board that there is room for computational chemistry or computational work in chemistry. And so this is where I'm going to switch over to another. How am I on time? Are you guys doing okay? This is the end of the chemistry portion of my talk, all right? So you did, can you all give yourselves a round of applause? I think you did extremely well. Very nice. And I hope that made sense to you all right? So now you get the chemistry that I do. Now I want to talk to you all and the adults in the room about some of my thoughts and how we can make science more exciting for you all, okay? And for those who are coming along. And so I'd like to talk about the media coverage of Gen Z. The majority of you in this room are Gen Z, all right? Anyone from any baby boomers in the room? No? Any silent generation, greatest generation folk? Any Gen Xers? Yes, I see some Gen Xers, okay. Any millennials? And finally, can I get a hand or raise a hand for the Gen Zers in the room? Literally all of you guys. Okay, So normally, and this part is really kind of just to tell you my thoughts on Gen Z, and also to, for the non-Gen Zers in the room to kind of appreciate and understand what, where the Gen Zers are coming from. So this is kind of the media coverage, at least in the US, of what you normally see for Gen Zs. Gen Zers make difficult employees, managers say, right? So nothing positive is basically what I'm trying to say. Keep reading. Gen Z branded the hardest generation to work with because y'all lack discipline. That's something that people say. Laziness highlights flaws in Gen Z. Apparently, you all are self-absorbed, screen-obsessed, whiny, privileged, entitled, and lazy. These are like newspaper clippings, okay? Not my words. Gen Z want to work less. And you're at the top of the boss's firing list, okay? So, not very good, right? Do you all agree with, I think you're probably like, that's not us, right? Yeah? So this is kind of the impression of this current generation. And I want the millennials to realize that you too got this, right? I'm going to get to a point here. Because if you look on the cover of the Time magazine in 2013, you'll see what they said about us, right? Millennials, that we're lazy, entitled narcissists, same words, who still live with their parents, facts. Not me, but some of my friends still do. Why they'll save us, right? And then there we are. Like, honestly, we're the originators of the selfie, by the way. Give us our props. And Gen Xers, I'm sorry, but you kind of got some flack too, right? Like the cover of the July 1990, laid back, late blooming, or just lost, right? Overshadowed by the baby boomers. So basically my point is nobody has anything good to say about the current generation, whatever generation they are, right? That's kind of like the going, like observation right here. And this is something that's been seen throughout history, and Professor Paul Ferrier, you Calgary, brilliantly combined these newspaper clippings over the years, where people talk about all generations being lazy and that nobody wants to work anymore. It makes me think of that Kim Kardashian video. Anybody knows what I'm talking about? She's like, nobody wants to work anymore. And so this is kind of this really newspaper clippings of what people said over the years, right? 2022. According to a new survey, 1 in 5 executive leaders agree that no one wants to work anymore. Nobody wants to work anymore. Nobody wants to work anymore. I mean, you can go all the way back to 1894. Nobody's ever wanted to work, apparently, right? It goes all the way back, right? So this is a common misconception that nobody wants to work. But I think embedded in here is why. Nobody wants to work anymore. In these hard times, and I think it's because of the wages, right? I think Gen Zers are like, we'll work, but you got to pay us, right? Our fair share, our dues, what we are worth, right? You're like, we're not going to work for starvation wages. And actually, this is really just a psychological bias, and I like to tell my colleagues that when they're like, oh, these kids today, they don't want to do any work. I'm like, it's a psychological bias that, society has been on a steady decline ever since the dawn of time. And that's not true, right? I mean, machine learning, I just talked about some amazing stuff people are doing. All the discoveries we've accomplished as scientists, we are making a lot of progress. So society is not on some steady decline. It's just this bias that we have, that, somehow the younger people aren't studying as hard as we were when we were in college. I'm like, did you see your friends who were not in the library with you? They were not good students, right, necessarily, right? So, and what it really means is we have to think differently about how we educate, right, the current generation, because you all are different people. Gen Z, my favorite generation, I have to say. These are some little bulletin, some points about Gen Z. Born in 1997 through 2013, all right? You all are digital natives, right? You grew up on your smartphones. As a matter of fact, your parents probably gave you the iPads to shut you up, right? So digital natives, shorter attention spans for sure, no question about that. But what I've learned from you all is that for you, technology is not a tool, right? It's just a part of your life, right? You can't imagine life without technology, many of you, right? You know how to use it, you know how to navigate it to get everything you want, right? Everything you want, you can get it on your phones or on your computers. You can get movies, you can get music, you can get even your academic learning, right? Everything is there, right? I mean, for me, I shop on Amazon. Like, if I don't get a package in a week, I have to find something to buy. It's really bad. I'm like, where's my next package coming from? But you all also are we economists, right? You're in the age of sharing. You like to share textbooks. You like to share Ubers, right, etc. But one thing that I've noticed about a lot of my students, at least in the US, is that they're very much deeply concerned about their future, right? There's really this energy among this younger generation where there's a lot of hope, right? You're like, the world is a mess. We don't have to even like convince each other about that. And so I think what that means is chemistry education has to change, right? I think it's very important that we reimagine how we mentor students, how we educate students. I think we have to start thinking about how we incorporate cultural and social issues in our classrooms. It's no longer a world that's disconnected. I think a lot of times people are like, well, I don't teach culture in my classroom. I'm like, yes, you do. You know, all of the chemistry examples and textbook are about baseball, right? So we also have to pay attention to students with historically marginalized identities. And I think a lot of students, some of you, many of you in this room will realize or appreciate or agree with the fact that, you know, we have not done enough, right, to work on the retention of students from historically marginalized identities. And if we want to do that, we really have to change how we educate and how we go about retention. And just want to point at a really amazing paper by David Asai that I think really brilliantly sums it up. And you know, he talked about the fact that the way we teach nowadays is, at least in the US, it's about deficit thinking, where we really blame the students in like, oh, you don't know enough. That's the reason why you're not doing well. Why is it that a lot of our students from historically marginalized groups are not we're not retaining them? It's not because they don't know enough. It's because of the culture that exists in many of our spaces. And how can we, you know, change that culture so that people can have more belonging, right, and so that they can thrive? And so I think we have to shift to an achievement model, like think about ways that make students excited about what is it that makes students achieve, and how can we elevate that over ways in which students do not fail, or ways in which students fail. And so these are some of the things I think we all need to work on. Teaching techniques. I'm very big now on making videos for my classroom. Also like representation in classrooms of like women, racial minorities, queer people. Also like incorporating issues, social issues in my classroom. Like when I teach about like cis-trans isomers, that's kind of when I talk about like cis-transgender identities. That's a way to like make chemistry kind of make sense for some people in the classroom. And then these other things. So I just want to talk about some really cool teaching techniques that are out there that I love. Everyone, you know, works on active learning these days. They're really neat. Multiple forms of engagement and assessment is a way that a lot of people are trying to get students involved, representation. But also really, I think with this age of like students always on their phones, that we really need to pivot to virtual types of video lectures, virtual reality podcasts, and even social media as a way for students to learn. Like, I've learned a lot on like Instagram, and for example, this is one of my favorite Instagram accounts, Zoom Orgo, and it's really neat. Literally, they post like a question, and you just answer it, right? So while you're scrolling, it pops up, and you're like, oh, which molecule is chiral? And you're like, oh, you know, and then you click on it, the answer is, right? Which one? Anyone can tell me? It's fine. We won't pressure you with that. But it's not C. It's definitely D. And so things like podcasts, right, are really neat that you can listen to learn about chemistry. My students, I make videos and post them, and they listen to them while they're walking, right? So like video lectures and different ways for students to really get to learn about chemistry without just always sitting in a classroom, right? So students learn really differently. And so the reason why is because, as I said, these are some crazy statistics. 3.5 hours on average a day that this generation spends on their phone. So I want to take the chemistry to you all, right? On your phones, you can watch chemistry, you can watch your regular videos, but you can also learn chemistry, right? And so I want to show you how some people do it. Anyone knows Chemical Kim? Anybody ever seen Chemical Kim? So Chemical Kim makes these really cool videos about like chemistry. And I just want to show you 3 videos that I think are really cool. So let's see if there is sound. Oops. Can you hear it?
Wow. Oh, wow.
This is just water. I'm gonna take some sugar, add it to the water, and mix it up. And
Oops.
yes, the apparatus is plugged in. In order to get this light to light, I need to get electrons to pass through these two black tubes. Sugar in water isn't providing those electrons. So let's try some salt. Put some water and salt together and make a salt solution. Ready for this?
Oh, wow.
Electrons, they're passing through solution, and that's because there's ions present in solution with the salt, where with the sugar, there's no ions present in solution. This is a fantastic
Anyway, I won't bore you with the whole video. But
test to check your compounds.
Oh, wow.
All right. You all know this one, don't you? I know you know this one. So
How to draw
this
the
next
perfect
one
picture.
is just
So
me
first you want to
drawing a
start drawing
chair,
two
and I'm like,
parallel lines
why
that are
did 3 million
slanted
people
and are
watch
at
me
a
draw a
60-degree
chair
angle
information,
approximately
right?
to
But
some horizontal
people want to
imaginary
learn
point.
about
Next, you want to
chemistry in
draw
different ways.
90-degree angles
I'm not going
approximately
to
with those
bore
two
you,
lines.
but the point
One
is,
like
I
that,
literally
one
just
like
drew
that,
a chair.
and then you want to connect them.
Anybody familiar with a chair here? So a chair is really just a
There you have it.
six-membered ring.
Next, you want to put in your
it's
axial and
three-dimensional
equatorial
structure,
bonds. You
right?
should have
It's
6
not
axial.
flat. And so this is actually how it looks in 3D.
3,
And this you have to
4,
learn if you take
5,
organic chemistry
6.
how
And
to
then you want to
draw
put your
this
equatorial
really
bonds in.
quickly.
And this
And
one,
so this
here
is
we
me
go,
just making a
maintain that
video.
angle.
How do you
Here
draw
we go
this
as well,
chair?
this
And I'm
one
explaining
here,
to people how you
this
draw
one
it.
here, this
I'm like, why are
here,
3 million
and
people
one
watching me draw
You can't
this?
see
You're
it,
definitely
you
not
can
3 million
NW.
organic chemists in the world. But anyway, this guy is genius, right? And a lot of students will watch this and they will get it. And a lot of my colleagues are like, I don't understand how, like this. I'm like, don't worry, this is not for you, right? And I mean, this is just brilliant. I mean, you can tell 22 million people watched the man explain this reaction. Let's hear it.
Alright, cool. Man's got some lithium metal there, innit? Rare thing, trust me. So obviously lithium's in group 1 like sodium, innit? So it's an alkali metal, you get me? It has a dark grey layer on the outside because obviously the lithium's reacting with the oxygen in the air to form lithium oxide, innit? But the inside is bare shiny and nice and that. Now, because it's on a group 1 thing, it's soft and squishy like sodium. Not as soft, but you can still cut it and that, you get me? Shiny settings, come on, you know what's going on. Alright, boom, so we're going to slap it into some water and see what I go on, innit? Obviously, man's just pouring it up, you done know. Alright, cool, let's go, yeah? Into the water. Alright, so we can see little fizzing going in and that, some gas being released. So that's hydrogen gas, innit? Now, the scientific term for fizzing is effervescence, you get me? So the lithium metal is reacting with the hydrogen and the oxygen in water to form lithium hydroxide. That's the alkaline thing, you get me? Come on, you know what's going on.
I mean, that was just amazing, right? And you all got it. And that's like some beautiful chemistry. We actually do this experiment in my when we teach general chemistry. And I mean, my students get more of a kick out of this than they do from me actually doing this experiment. So that's just really just showing you some ways we can like think about reaching students, you know, in the way they learn and more visual aids that can help students. And so I then, as a result, decided I'm going to start making videos too online. And so I make a lot of videos with my students just to show growth mindset, to show, you know, authenticity. Because I think the other thing we have to do as educators, right, is to be authentic when we teach. So students can feel as if their faculty or their teachers have a growth mindset and they believe in them. And that's one thing with this younger generation. I think, you know, my students are not very resilient because they're not very hopeful. I think a lot of times we need to remind students that you can do this, you can support, I'm going to support you, right? I'm going to help you along. And so we make videos like this. I like to showcase like me interacting with my students in class. And then also the classroom ecology. I think we have to really work on how we build a classroom of students who are in a community together, because oftentimes we forget that as a whole, we need to be there for each other, and students need to work together, and everyone needs to be committed to the advancement of each other. And so, you know, we make videos in my class, like for example, this one, we're just doing a little bit of a dance to this Doja Cat song. Hey, all right. It's a little dance break, right, in lab. And I think that's really neat to kind of like, you know, have fun. Chem lab is a place to have fun. It's not a place to just be, you know, boring. I think we have to make sure students understand that chemistry is fun. You can have a lot of fun. You can be your authentic self. You can be who you are. And you can become a great scientist. So for all of you who think that science is not accessible to you, it is, all right? And I want you to remember that the field is changing in a number of ways. We want you to be a part of it. I want you all to bring your full authentic selves, whatever that is, to science, because we need you all. You are the future. And thank you for having me. And I'll take, I guess we're not doing questions, but thank you.
We are definitely happy to take questions. If anyone has questions,
sure.
yeah, raise your hands. And we've got Dara and Pete are wandering around with mics, so please go for it.
Oh.
Yeah, nice try.
Any questions? Anything at all, doesn't matter. I talked about 3 different things. I talked about me, I talked about chemistry, I talked about my thoughts about you. Yes?
That was fast. Sorry, that was very fast. What changed your mind about organic chemistry?
I think what made me love organic chemistry was really my teacher. I think it's so important to have educators who are committed to explaining things to students in a way they understand and find resources for them that work for them. My college professor was just really, really good at explaining organic chemistry. And so that was really what did it for me. Yeah. I also like organic chemistry because it's like puzzles, right? For me, it was just a big puzzle, and you could just stick molecules together like I showed you, and just learning different ways you could do that. So it was just exciting, a big puzzle for me, yeah. I think that's just how my brain worked. Yeah, I like that. I like remembering like random facts and like connecting things. Like one of my weird obsessions is planes. I'm like, 6 wheels. That's a Boeing 777. It doesn't make sense, you know, like connections. Making connections is kind of an exciting thing for me.
You told us about antibiotic resistance. Do you have something about viruses, like
I'm sorry. Oh, I'm not really hearing you.
Like your lecture was about the cycles, your molecules in the antibiotic resistance of bacteria. Is it something similar compounds for viruses, like in the context of coronavirus or something?
I mean, there's a lot of work on coronaviruses, right? And viruses and bacteria are fairly different, so you kind of need different solutions. So, I mean, the mRNA route that a lot of people have used right now, right? Pfizer and other companies have seems to be a pretty good approach. Of course, like bacteria, these viruses can become resistant to that treatment, and then you have to make new ones and evolve it. That we see nowadays. We're probably on what version? Who knows, 8 or 9 for addressing these coronaviruses as they evolve, right? So different solutions, but similar thought process, right, around evolving the solution.
Okay, so we are at 5:30, so if people need to go, please, you're very welcome to. I'd love if we can all thank Dr. André Isaacs again, that would be magical.